Okay, good morning, everyone. Good morning.
Good morning again, sir.
Okay,
Hmm. Sir, good.
Okay. Portrait. Look.
okay, so maybe I'll check the attendance later after our discussion. May I start our lesson for today? Okay, so
Go
please
ahead,
turn off.
sir.
Okay, so please turn off your audio while I am discussing, and also you can turn it on if you have some questions. So last time we discussed our topic in module one about the data analysis and on how to predict using a regression method. We also understand what the data analysis is and how this data becomes part of our daily life. In today's topic, I will be going to discuss the two main objectives of simple linear regression, and also we're gonna run on example that will help us start understanding how should we interpret the coefficients of a simple linear regression model. So simple linear regression or regression models in general have two main objectives. The first one is going to be to establish if there's a relationship between two variables. We're going to be talking about the positive relationship between two variables if they tend to move together in the sense that when one increases, the other one increases as well. And conversely, in a negative relationship, we find that if one variable's values increase, the other variables tends to decrease. More specifically, we're going to be talking about statistically significant relationships between the two variables, but we will get back to this later. Let's talk about some examples. On average, we expect that peoples and families that earn higher income will generally spend more of a given product. In this case, we're talking about a positive relationship between income and the spending. We could also analyze and test if there's a relationship wage and gender. Okay. Um, we could ask if are men likely to earn higher wages than women. Case in which we're talking about gender discrimination, which is negative and we don't want it. But we can actually use the regression models to test if that relationship exists. Okay, and another example that hope you find odd is relationship between students' height and that some students' exam scores. We should expect no relationship to exist, and we can use for regression models to test that. Our second objective is going to be to forecast new observations. And what we mean here is, can we use what we know about an existing relationship to forecast and observe values? Let me give you a couple of examples. Like for instance, if we know that our sales tend to grow over time, and we actually even know how strong this relationship is, and we know how fast our sales grow, we could use this information to predict or to forecast what will our sales be over the next quarter. Also, if we have data on stores and we know how profitable different stores are, and we know what is the relationships between how much competition a store is facing in a given location, or what the population or of a location is, and how those variables impact the store profitability. We could use what we know about previous stores to evaluate the profitability of a new inexistent store. Of course, we don't know how profitable new store is going to be. But if we know how much competition is going to face, and we know how much people live nearby the store, then we can use this information that stores profitability. Okay? In general, we're going to be talking about two variables. And I'm sorry that I did not include it to my presentation here in my PowerPoint, but please listen carefully and you can also jot it down on your notes. Okay, so there are two different roles that variables play in regressions models. The first uh, is going to be a dependent variable. This is the variable whose values we want to explain or forecast, and we call it dependent variable because its values depend on something else. We will be denoting it as y. The other one is that the independent variable. And this is the variable that explains the other one. And we say that its values are independent, hence its name. Then we will denote this value as x or this variable as x. When we use simple linear regression models, we call them linear because the magic is that we're using a linear equation. And from your high school years, you might remember one of these, where y is a function of x. And there's a term that is added to the function, another one, that multiplies the x. In the stats world, we like Greek letters. And we're going to be using a slightly different notation. Our linear equation is going to have a beta zero term, which we're going to be calling the intercept or the constant. And the beta 1 here is, which is the term that multiplies to x. And we're going to be calling the coefficient of x or the slope of x. And as a recap, we call these linear equations because they will appear as a straight line if we plot them in a dimensional plot. Let me show you an example of a linear equation. And remember, our model is y is equals to beta 0 plus beta 1 times x. Okay, and let's give numbers to those beta. And let's say that we have a linear equation y is equal to 4 plus 2x. Okay, so let's analyze what the 4 means. 4 is the distance from the horizontal axis at which the line crosses the vertical axis. In this case, if x had a value of 0 here, of y equals to 4, here is the 4, and we see here that is crossing the vertical axis. 4 units above the horizontal axis, and the slope in this case is a 2. And it means that for every unit increase of x, and y will increase twice as much or 2 times as much. We see here that x increased from 2 to 4, while y increased from 8 to 12 twice as much. Let's further understand this wonder, what happened if we change the intercept. In particular, let's use a larger intercept, like for example, we change the intercept to 9, and we see that we're moving line upwards here, meaning that we're increasing the distance from horizontal axis to the point where the line intersects the vertical axis. We could also have a negative intercept which would imply that the line is intersecting the vertical axis dito sa baba below the horizontal axis at a negative number. If x were 0 here, y is minus 2. Now, what happens if we change the slope? If we change the slope, we're changing the sensitivity of y on values of x, meaning how fast or how slow the y will change when the unit of x is changed. If the slope were 5, that means for every unit of x, y is going to increase 5 times. So you see that we have much steeper slope because y is growing faster than it was before when we had a 2. And what would happen if we had a zero slope? Ano mangyayari kapag zero yung slope natin? So this would mean that it doesn't matter what value x has, y will always be 4. And if you go all the way around to a negative slope, a minus 3 in this case, here, we have a downward slope. To, and this represents that y will decrease 3 units for every unit of x. Now in this case, we're talking about very crisp and clear straight line, but data in the real world does not behave like this. Okay, so data in general is going to be a series of x and y observations, and that on average may follow a linear pattern, and that's why we use linear regression models to represent that. But the line is not always, and actually most generally, not interesting or passing across the dots. Rather, they're gonna be errors, and we can measure which are the distance between the dots on the real life. And the actual linear regression, and what linear regression is going to do is to try to draw a line and that minimizes these errors. But the important aspect we're going to take away now from this is that our linear regression model must include this error into it. Okay, so this is how our linear regression model looks like. It is y equals to beta 0 plus beta 1 times x plus the error term. So let's recap. The y is the dependent variable. This is the variable whose value depends on all other parameters in the equation. And x is the independent variable. It helps to explain the variance in the y. And the beta 0 is our constant term or intercept. Meanwhile, beta 1 is the slope coefficient for the x, and epsilon, which is a Greek term to symbolize something that is very, very small, is going to be, and our term which we're trying to minimize. Okay, so now let's look at an example which I have uploaded it on my YouTube using the Google Colab. We will trying to predict using Python codes, and I have here the video. So please try to understand, and you can jot down notes as well. Okay, any questions in our discussion? Anyone, any questions? So I have your video, so iti-play ko siya sa YouTube. So please try to understand how to apply the regression model or simple linear regression model using Python codes in Google Colab. Okay? Then I would like to share my screen now.
Good day, everyone. In this lesson,
Um, nakikita ba yung video ko?
Yes po.
Kita, sir, kita.
Okay. May sound
I'm
ba?
gonna show you how to implement a linear regression
May sound?
Mahina, sir.
May na.
Mahina, sir.
in Python using Google
Okay na ba?
Colab. Actually,
Mahina,
Google
sir.
May na pa din. Baka yung ano nyo, yung sound nyo sa ano.
Full na nga, sir.
Colab is a
Full
powerful
volume
tool
na,
to
sir.
code any kind of
Okay, so please
Pwede
wait.
na yan, sir. Ano na lang.
Pwede na. Actually, meron din akong link na nilagay dito sa module to natin. You can watch that video. As well as the Google Colab on how to use the Google Colab in Python. Okay?
Good day, everyone. In this lesson, I'm gonna show you how to implement a linear regression in Python using Google Colab. Actually, Google Colab is a powerful tool to code any kind of programming languages, which you can access freely using your desktop or your mobile phone. I will send a tutorial video later on how to use the Google Colab. And now, it's time to start implementing linear regression in Python. Basically, all you should do is apply the proper packages and their functions and classes. The package NumPy is a fundamental Python scientific package that allows many high-performance operations on single and multi-dimensional arrays. It also offers many mathematical routines, and of course, it's open source. The package scikit-learn is a widely used Python library for machine learning built on top of NumPy and some other packages. It provides the means for pre-processing data, reducing dimensionality, implementing regression, classification, clustering, and more. Like NumPy, scikit-learn is also the open source. If you want to implement linear regression and need the functionality beyond the scope of scikit-learn, you should consider stats models. It is a powerful Python package for the estimation of statistical models, performing tests, and more. It's open source as well. Let's start with the simplest case, which is simpler linear regression. Then I will open here the Google Colab. Just type Google Colab on your Google browser. Then I have here my works here. So actually there are 5 basic steps when you're implementing linear regression. The first one is to import the packages and classes you need. Number 2 is to provide data to work with and eventually do appropriate transformations. Number 3, create a regression model and fit it with existing data. Number 4, check the results of model fitting to know whether the model is satisfactory. And number 5, apply the model for predictions. So I will open here my first work here. Okay, so these steps are more or less general for most of the regression approaches and implementations. Step 1, here I have here the title, which is the simple linear regression with scikit-learn using scikit-learn. Okay, so first one is to import packages and classes. The first step is to import the package NumPy here and the class linear regression from sklearn model here. So now you have all the functionalities you need to implement linear regression. The fundamental data type of NumPy is the array type called NumPy and the array. The class sklearn that linear model, that linear regression will be used to perform the linear and polynomial regression and make predictions accordingly.
Step 2 is to provide data. This second step is to define data in order to work with the inputs regressors X here and the output, which is the predictor Y. So here is the our regressors and here is the predictor. Okay, this should be the arrays. The instances of the class numpy that and the array here are similar objects. This is the simplest way of providing data for regression. So I have here the code. So if I would like to uh, click this button, so first we have to run this first. Okay, we'll wait to create the check here. So it means it's finished. Okay, so here, and next, let's us check here the code. Okay, then now you have two arrays, the X and Y array, or the input X and the output Y array. So you should call that reshape here. Why we should have to write the reshape here in X? Because this array is required to be two-dimensional, or to be more precise, to have one column and as many rows as necessary. That's exactly what the argument -1 and 1 of the three shapes specifies. There. So let's try to run the X and Y by using the print method. Okay, by using this code, let's try to run this program. So here is the output. Okay, here. Then let's try to print the Y. Yes, this is the result. This is for the X and this is for the Y. As you can see, X here has two dimensions. And X that shape is 6 and 1. I mean, 1, 2, 3, 4, 5, 6 rows and 1 column. While Y here has a single dimension and Y that shape is equal to 6. 1, 2, 3, 4, 5, 6. So the next step is to create a model and fit it. Okay, so first, this step is to create a linear regression model and fit it using the existing data. So let's create an instance of the class linear regression, which will represent the regression model. So let's type here the model linear regression. Let's try to run this. Okay, so these statements creates the variable model as the instance of linear regression. You can provide several option parameters to linear regression. First is the fit underscore intercept. It is a Boolean. It is true by default that decides whether to calculate the intercept 0, which is true, or consider it equal to 0 or false. Or pwede ding normalize, which is a Boolean, false default, that decides whether to normalize the input variables, or true, or not, it is false. And copy underscore x is a Boolean also, true by default, that decides whether to copy or true or overwrite the input variables or false. And n jobs is an integer or none or default and represents the number of jobs used in the parallel computation. This example uses the default values of all parameters. So it's time to start using the model. First, you need to call the .fit on model here. So model.fit x and y. Let's try to run this. Okay, here is the results. So with the using the .fit, You calculate the optimal values of the weights 0 and 1 using the existing input and output x and y as the arguments. In other words, that fits the model. It returns self, which is the variable model itself. That's why you can replace the last two statements with this one. Model is equal to linear regression that fit x and y. Let's try to run this. So this statement does the same thing as the previous two. Here, 1 and 2. So it's just shorter. So pwedeng to or pwedeng ding ito. Then step 4, get results. Once you have your model fitted, you can get the results to check whether the model works satisfactorily and interpret it. You can obtain the coefficient of determination R squared with that score here on model. So let's try to run this sample. Okay, R underscore squared is equal to model that score x and y run in the program. And let's use the function print for coefficient of determination. So here is the result coefficient of determination 0.71. Okay, so when you're applying that score here, the arguments are also the predictor x and regressor y. And the return value is r squared. The attributes of model are that intercept here, which represents the coefficient 0, and that coef, which represents 1. So let's try to run this. So this code illustrates how to get 0 and 1, and you can notice that that intercept is a scalar, while that coef is an array. The value of 0 is equal to 5.63 approximately. Illustrates that your model predicts the response 5.63 when x is 0. And the value for 1 is equal to 0.54. Means that the predicted response rises by 0.54 when x is increased by 1. You should notice that you can provide y as a two-dimensional array as well. In this case, you'll get a similar results. So this is how it might look. New model is equal to linear regression that fit x and y that reshape -1 and 1. Print intercept by using intercept and this look for that intercept and that coef. So let's try to run this. Also this. We will get the result 5.63 for intercept. And here for slope, the 0.54. As you can see, this example is very similar to the previous one. But in this case, that intercept is one-dimensional array with a single element 0. And that coef here is a two-dimensional array with a single element 1. Okay, so step number 5 is response. Predict response. So once there is a satisfactory model, you can use it for predictions with either existing or new data. To obtain the predicted response, we will use the that predict. So y underscore predict model that predict x. Use the function print and predicted response y predict and this code. So let's try to run these two. And here. Okay, so we have the predicted response of here. Here's the result. So when applying that predict that you pass the regressor as the argument and get the corresponding predicted response. So this is a nearly identical way to predict the response. But what about for multiplying the each element?
Bilingon hagin didikit. Sige! Hello sir, na-mute po.
Yung iba paki-mute muna. May sound pa ba?
Nawala po sir.
Walang sir.
Yung nag-interrupt kasi kanina na gano'n eh. Saglit lang ah. Okay. And okay na ba? Add model that intercept okay na to the product. The output here differs from the previous example, only in dimensions. Here, same as here. The predicted response is now a two-dimensional array, while in the previous case, it had one dimension. If you reduce the number of dimensions of x to 1, these two approaches will yield the same result. You can do this by replacing x with x dot reshape to -1 or x dot flatten or x dot revel when multiplying it with model.coef. In practice, regression models are often applied for forecast. This means that you can use fitted models to calculate the outputs based on some other new inputs. So let's try to run this code. We will get the result 0 to 4. And for y, so here is the result. So here, the depth predict is applied to the new regressor x new here and yields the response y new. Here is the response. This example conveniently uses a range from numpy to generate an array with the elements from 0 inclusive to 5 exclusive. That is 0, 1, 2, 3, and 4. Linear regression is sometimes not appropriate, especially for nonlinear models of high complexity. Fortunately, there are other regression techniques suitable for the cases where linear regression doesn't work well. Some of them are support vector machines, decision trees, random forest, and neural networks. These are numerous Python libraries for regression using these techniques. Most of them are free and open source, and that's one of the reasons why Python is among the main programming languages for machine learning. The package scikit-learn provides the means for using other regression techniques in a very similar way to what you've seen. It contains the classes for support vector machines, decision trees, random forests, and more. So now you know what linear regression is and how you can implement it with Python and the three open source packages using NumPy, scikit-learn, and stat models. You use NumPy for handling arrays. Linear regression is implemented with the following. First is the scikit-learn. If you don't need detailed results and want to use the approach consistent with other regression techniques, you can use the scikit-learn. But if you need the advanced statistical parameters of a model, you need the stats models. Both approaches are worth learning how to use and exploring further. When performing linear regression in Python, don't forget to follow the steps. First is to import the packages and classes you need. Second is to provide data to work with and eventually do appropriate transformations. Step 3 is to create a regression model and fit it with existing data. Number 4 is to check the results of model fitting to know whether the model is satisfactory. And step number 5 is to apply the model for predictions. So that's all for our linear regression. So thank you. Okay, so you may now turn on your video and audio. Is there any question, Roel?
Sa, hindi mag-open yung akong ano.
Okay, please turn on your video.
Turn on your audio.
Video.
Sa picture.
Turn on the picture.
Is there any question?
Marami pong din sir na katanungan sa isip ko.
Question, sir.
Doon sa video, pwede nyo
Possible po ay
Aabutin
aabutin
siguro ng
siguro ng
2
2
days.
days.
So,
Magsila.
yun.
Sana. Ping, ping gano'n.
Meron ba?
Kasi mag,
Ay, sir.
ano pakita lang.
Pa-close mo na ng audio.
Binor na surprise.
Turn on mo na ng audio.
Nari ako.
Ano pala, turn off. Yung audio lang. Audio.
Yung audio daw.
Maximo, gilingaw-lingaw ni Maximo.
Iwan sana.
Okay. So, okay na. Okay, so I will upload this recording your GC so you can follow. Baka may mga topics doon na hindi kayo naliwanagan, so pwede niyong pakinggan ulit. Or kung meron kayong mga katanungan, pwede din naman na pumunta dito sa school or mag-ask sa akin. Or pwede din naman na i-chat ako. Ganun, so para for another information. So doon sa topic natin kanina, linear regression pa lang yun. Wala pa yung logistic regression. Okay, maybe we'll set a meeting next week for logistic regression. Okay lang ba?
Yes, sir.
Hello sir.
Okay lang.
May tanong po ako, generally lang po na tanong. Isa lang. Ano po yung pinaka kahalagahan niya saan siya ginagamit, no? Yung linear regression po.
Yung linear regression, ginagamit siya for forecasting. Nakikita niyo ba yung mga news about sa weather forecast?
Yes, sir. Yes, sir.
Diba? Kadalasan
Okay po.
ginagamit yan doon. So,
Yes,
pwede din natin gamitin for prediction. Like for example, ipipredict natin kung ilang yung about sa gender, yung scores, yung ratings. So, yung ganun. Meron akong isi-shared na pictures ng linear regressions examples. Ito. Nakita ba? Okay, so ito yung mga
Yes, sir.
example ng mga linear regressions is all about plotting. Meron tayong fitted line, pair plot. So para ma-predict natin yung gusto nating i-predict gamit yung linear regression. Okay? So straight line yan. Okay. So gamit yung Python codes, pwede kayong makapag-create ng ganitong plot. Okay? So for
Okay po,
forecasting. Okay, so other question? Baka may question pa dyan. Wala na ba?
Pag binalikan po namin, sir, next year yung professional elective 3, ganyan din po yung topic.
Yeah. Actually, yung IT Professional Elective 3 is bagong subject kasi ito eh.
Opo.
New subject. Yeah. About mathematical or data analytics operations.
Opo.
So,
Natanong ko
ganun pa
lang
din
baka
yung
may plano si Maximo.
Tanaw, Sir Aison.
Sir, ayayo.
Okay, so any questions regarding our topics?
Wala, sir, wala.
Okay na? Okay, so kapag wala na, so please turn on your video. Picture taking.
So,
Yo, Kevin, no? Splitin.
Tanaw, yes, Sir Ice.
25 lang tayo lahat, no? Yung attendance nyo is dito ko na lang siguro i-check kasi makikita ko naman yung mga names nyo. Okay? So,
Yes, sir.
Roseanne, paki-on yung video natin. JBan, ano? Ronic,
Ay,
Papiloni.
Jeremy, ka na.
Benson, JBan, Zanen,
Hindi po, sir, maglabas ang iyan ng video.
si Zanen. Okay, sige.
Opo.
Okay na, so picture taking, 1, 2, 3, smile. Kidutin ko na ba? Oh, si Benson.
Ay!
Waki-waki.
Social
Okay,
distancing.
Social distancing. Wait lang, sir, ang kape.
Okay, so 1,
Kevin,
2, 3, smile. Smile. Okay na? So, thank you. Thank you, class.
Thank you, sir. Kevin, Sir Aison.
Okay, so, ingat. Take care.
Benson,
Bye,
hindi
sir.
ka na nakaluwas.
Bye.
1-0.
Benson, hindi ka na nakaluwas. Huwag ka kapapaltak.
1-0-6-1.
Hey, Jeremy, ikaw mo.
Wait
ka na.
Makakate mo?
Pwede na maglat, sir.
Gusto mo?
Jess,
No?
hanap ka lang daw. Sir.
Wala yung nag-isip-silipan ako na.
Tapos na na.
Makanta na kita. Babay na sa Indo.
Para na anak ka na serious